Hi everyone. To find phonon and some basic thermodynamic property using some DFT code like quantum espresso, BASP, C star, then you may heard about the Phonopy code, which is a Python-based program and helps you to compute phonon as well as some thermodynamic properties. You may find this documentation in their website where they describe how we can utilize Phonopy together with the DFT to find the phonon and the thermodynamic properties. When I came through all this documentation, then I came to know that they implement the two approaches to compute phonon. One is the finite displacement method, where the idea is that the system that you have is displaced finitely and force is created there, which is further utilized to compute frequencies and further integrated to compute thermodynamic properties. But this steps involves a lot of the process that you need to go through. First is to create the supercell and the displacement using the Phonopy, and then you will see a lot of displaced input file structures where you need to reorder them in systematic way in specific folder, and you have to run your DFT inside the folder, and further you need to extract the forces from the output of the DFT run that you had done, and finally you can compute it to obtain the frequencies, phonon, and other thermodynamic properties. So this steps involves a lot of time, and here in this video, to remove all these grueling steps, I have designed some basic script that you can use to compute phonon easily. So the idea is that we will use some pre-processing script and post-processing script, and between these two scripts we need the JavaScript to run the DFT computation, and this is just a JavaScript that commonly you can use to submit your job in your HPC. So the two script that I have here is everything for the phonon calculations. So let's start with the pre-processing script. So in pre-processing script, what we have to take care is that the dimension of the supercell that you wish to create, and for this particular demonstration I have a 2D system made from aluminum, carbon, and nitrogen. So I will use focus 1 to create the supercell and the displacement. So this script will do the displacement and create all the displaced file arranged in a specific folder where we can run the DFT using the script number 2. Okay, so let's do it practically here. Now I'm running the first script simply by this. So just running this script, we can see it created 18 individual folder, and it depends on the number of folder depends on the number of supercell and the system that you have, so no worries about this. Maybe if you use your system with supercell, let's say 2x2x2, then it may create maybe 20, maybe 40, maybe 100, and that depends on the system's nature, so nothing to panic about it. But the good thing is it created already all the displacement and copied all the input file necessary for the DFT run in each folder. So you can see now this script has utilized all the inputs necessary for your DFT to copy inside all individual folders. So we are ready to go. Now the second task is to run the DFT in your HPC. So for that you need to submit your job using the script, script number 2.job.sh. So you can submit your job with whatever command you are comfortable with or utilizing there. Let's say like this, and of course this is the time consuming part. It takes a little bit time to compute the forces, and in this particular video I have the result already here so that I can show you very much quickly. Okay, so the results are here in the output folder. So once your DFT computation is done, you can see the output inside each of the folder, and of course you are ready to extract the force constant matrix from the DFT run. So it is done by script number 3. So we have the script number 3 here ready. I just deleted script 1 and 2 because we don't need that anymore. Now let's run the script number 3, which gives us the Phonon diagram in terms of the matplot, as well as it gives us the XM grid plot and some data for thermodynamic properties computation. So let's run the script number 3. So okay, so yeah, here we go. We can see the Phonon here. The Phonon high symmetry points are clearly observed here, and we can see the PDAS attached on the right, which is of course the Phonon PDAS, and the plot is good. So yes, in addition we obtain some Phonon plot here with XM grid format, where you can do editing and make your plot according to your wish, and you can save it as AGR or EPS or any format. And yes, of course you will have the thermodynamic output here. You don't need to do anything except plotting here. So you can remove this and can plot with XM grids or with any of your favorite plotting software, maybe Origin, maybe I don't know, maybe you can even use the Python script and so on. So let me just show you some quick result that we can obtain here from this computation. Okay, let me just choose this thermo.out. Okay, so okay, let me import all the data. So this must be the free energy, and 1 versus 3 must be entropy. So the entropy goes like this, 1 versus 4, and this may be, I don't know, I will see that specific heat capacity, I don't know what is in there. So these are the plots, thermodynamic plots that you can play with, and you can plot and make according to your desire. You can play with it, you can make it whatever you want. So I think it is pretty much done. So this is thermodynamic result. You can just label it and make it suitable for your work. So one thing I would like to mention here is in script number 3 you need to be careful about some important thing, that is you need to provide it the number of folder that you have. So it starts with number 1 and goes to number 18, so you need to provide this information here. And another thing is you need to provide the supercell dimension and the high symmetry path, and if you want to label it then just write like this. And also you need to be very careful with the conversions of these band points and this MP points, and similarly here. So careful with that. Let me show you how this value can affect our result. So instead of MP61, let me use 10. So how the band will appear, let me use that and show you. So when I just use that, and the computation is so fast, but the result might be not noticeably changed, but there is some change of course, but the values of the bands are still high, so the result is not so different. But if I reduce the band point less up to 10, then I'm afraid I will get different result. Okay, now yeah, the result seems a little bit different, but not drastically different, but there is of course the difference you will see anyway. So yeah, of course, same thing you can observe here in the XMGS plot. So okay, so that's it. So this is the super easy method that I described to you practically, and hope you like it. And of course I will be continuing making this kind of exciting things to you, and if you like this video, this kind of work, then you can connect with me by subscribing. And for the script, you can email me, or maybe I will provide the link of my GitHub from where you can download it. Okay, so thank you for watching.